Hi, now we're going to talk a little bit more about how to use your periodic table and a little bit more of a reminder on the atom. And I just love the video, or the picture that I got from Facebook of cats. And that is so true. Cats are liquid, aren't they?
They do take the shape of things.
So I'm Kathy.
I'm John.
I'm Stephanie.
And we're here to run through this video for you. So in the previous modules, you learned a little about the atom, so we want you to recall that protons and neutrons are in the nucleus. You see that little picture over there? Those are the protons and neutrons. And that the number of electrons is going to be equal to the number of protons. And the electrons are those things flying all around. And electrons are in that space around that nucleus. We talked about electrons in that last set of videos. So keep in mind that a proton has a mass of 1 and a charge of +1. A neutron has a mass of 1, but it's free. It has no charge.
It's free.
And an electron, technically for us, really doesn't count. But if you're a physicist doing research, you would be weighing that up. But it doesn't really work in 104. But it does have a charge of -1. And that's really important. So all atoms of the same element have the same number of protons in the nucleus.
And your atomic number represents the number of protons in the nucleus. Versus your mass number is the number of protons plus the number of neutrons. So if you look at your mass number, you're essentially your atomic number plus the number of neutrons.
Equals the mass number.
Equals the mass number.
And we did that on the last slide by subtracting to get the number of neutrons. So if we have X to be the symbol for the element, and we look at our periodic table, you're going to see the mass number up near the top and the atomic number near the bottom on most periodic tables. So if in these examples for hydrogen, it has an atomic number of 1 and a mass number of 1.
Boron has a mass number of 10 with an atomic number of 5. Magnesium has mass number of 24 with atomic number of 12. And uranium, mass number of 235 with atomic number of 92.
Whoa, that's a heavy one.
Yeah.
It's a lot of neutrons.
Exactly. And neutrons and protons are all in the nucleus. So in neutral atoms, it's important to remember, this is kind of key, and this will be important in the next set of modules, the number of electrons has to equal the number of protons to be neutral. The charges have to cancel each other out. Okay, so remember, think about it means to take a little pause, to sit down and, think about this. Go ahead and do your math. How many protons, neutrons, and electrons are in this? Okay, so we lost our key. We'll
That's
have to
okay.
do this.
I think we can figure
You
this
think
out.
we can figure it out? Okay, so for PT, so hit pause and figure this out. Now we have our answers for you. We're going to write them in. Bear with us with this pen thing here. We're experimenting.
Okay, so for platinum, we know that the atomic number is equal to the number of protons. So our protons will be 78. I'm going to go ahead and write the electrons now because we automatically know that the electrons are there are 78 of those electrons. And now I have to figure out how many neutrons there are. I can go over here and subtract and get 117.
And you did that without your calculator. I'm impressed.
I have the key here.
Oh, that helps.
Okay, so now in argon, we'll do the same thing. We have the atomic number is 18, so the number of protons is 18. We know that then there are, whoops, that's not a P. We know that we have 18 electrons to make a neutral atom, and we can do our subtraction to get 22 neutrons. Would be N.
Sure. Excellent. Very good, Stephanie.
Thank you.
So these are very simple questions. Practice them because you may see them again somewhere, like on a quiz. Okay, so we're going to focus on that atomic mass. The atomic mass unit is an AMU. And I'm giving you this example not because you need to write it to a note card and use it. It's just to give you an idea of how small 1 AMU is, to help you remember how small, how tiny those atoms are. So the mass of a single carbon atom that has 6 protons and 6 neutrons is exactly 12 AMUs. I say exactly, but don't share this with the physicists who measure things to like 20 decimals. So for our purposes, it's 12 AMUs. And I'm going to throw up here this whole problem all done, but you don't have to do this. I'm not going to ask you to do this in class. If you have a mass of 12 AMUs, what would that be in grams? And I'm going to use my factor of 1.6605 times 10 to the minus 24 grams, plug it into my calculator, and I come up with 2 times 10 to the minus 23 grams. So let's see, that's 0.0000. Okay, that's too boring. But it is a lot of zeros until we weigh out 2. And I'll put that there. So significant figures, you know. And we are not going to be able to find a balance to weigh out a single carbon atom. So just keep in mind they're very, very tiny.
Thank goodness for scientific notation.
Yes.
I'm so glad to hear you say that. Yes. So take a look at these 2 atoms of boron. The cloud there that you see are the electrons. That doesn't mean it has a million electrons. That just represents the area, the basketballs that those electrons are in. Okay, so study this for a minute.
So are all those colored atoms, what are they supposed to be?
I didn't do a key. Yeah, the green atoms. Let me just write this on here. The green. I'm sorry. The green
Gray.
dots. The green equals protons. Did I do that right? No, the green
Actually, that would be
equals
neutrons.
Sorry, neutrons.
Yep.
I should have done this ahead of time. Sorry, guys.
No
And the red equals the protons.
All right.
Oh, that was a pretty darn good hint. So study the protons. Yes.
Looks like they both have 5 protons. Oh, wow.
You're exactly right. What is the difference between these 2 atoms? That's a little harder.
Well, looks like the left one has 5 neutrons and the right one has 6 neutrons. So they have different amounts of neutrons.
Perfect.
Oh, that's where the 10 and 11 come from.
Oh, wait a minute. There's my misprint. And you know what? I need an editor. One has 5 neutrons and the other has 6 neutrons. Thank goodness for this pen that I'm struggling with. Sorry, bad editing. All right.
Everybody
I'm going to move on
mistakes.
before I get caught on something else. Okay. So
scientists have found that there are 2 different types of boron atoms. One has 5 neutrons and the other one has 6 neutrons, just like we saw on the last slide. They both have 5 protons, though, so we know that they're both boron. We call these elements, most elements found on Earth occur naturally with 2 or more types of atoms, and we call these atoms isotopes. Isotopes are atoms with the same number of protons, but a different number of neutrons. So boron 10 and boron 11 are isotopes. They both have 5 protons, but they have different numbers of neutrons.
So Kathy's writing in here her little pet thing. Copy these by hand to a note card. Copy this definition. Anytime you run into a definition in chemistry, remember, we are teaching you a foreign language. We're going to expect you to have this mastered, these definitions mastered by the quiz. So copy them to your note card, notebook, whatever. Boron isotopes, the 2 boron isotopes are boron 10 and boron 11, as we have just seen. But if we look at the periodic table, we see that all of those masses on the periodic table, I know this is kind of tiny, none of them are just one or the other. There are a lot of decimals.
Boron says 10.81.
Wow. Well, let's take a look. When you look at carbon, for example, we see carbon is 12.0111, but carbon has 6 protons and 6 neutrons. How can that be? Well, it's because of the numbers of isotopes that are present in carbon. So the mass number on the periodic table does not equal 12 exactly because we have to take into account those isotopes. So if I took a scoop of boron atoms, I could actually get a pair of I like to imagine this a lot.
Yeah.
Atomic-sized tweezers and a huge microscope. I could ideally, theoretically, pick out a boron with 5 neutrons and a boron with 6 neutrons. And I could separate them into piles because they would be 2 unique types of atoms, but they're all still boron atoms. But the weight of that scoop of boron atoms would be contributed by both of those isotopes. So, if I gave each of you two 100 atoms of boron randomly, taken from that, 100 atoms of boron randomly taken from, commas are important, randomly taken from that scoop, and had you separate them into types, you would count exactly 80 atoms of boron that have 6 neutrons and 20 atoms of boron that have 5 neutrons. Right? If we calculated simple average, now simple average means take the total divided by the number, right? So simple average, that would give us an average weight for that element. And that would look like this. But we saw in the periodic table that the weight of boron was actually, what was it, Stephanie, 10?
10.81.
And so we know that this, to take a simple average, that would be incorrect. Because this would imply that there are 50-50 of each type of atom, and we know now that that's false. So scientists never do anything the easy way. Scientists like to do things, well, the correct way. Sometimes that's a little harder.
Yeah.
So what we're going to look at is what scientists call a weighted average. And that's important for students to keep in mind, that it's not an average of all the weights, it's a weighted average. I like to kind of compare it to your grades. So if you took a simple average of your grades, you'd add up all of the scores you got in the term and then divide on the number of assignments. Like, for example, 4 quizzes, 10 homework assignments, and 8 lab grades plus a final exam, I think I counted up equals 23 total assignments. Add up that. So wouldn't that be a great way to just do it? Just take all of their scores and, but no, we have to do things the hard way.
Oh, but then you could just do a homework assignment and it would equal the final exam.
And we don't like that.
Yeah.
Absolutely. Nope, that's not going to happen. So we need to give some assignments more weight than other assignments. Now, it's not like, it really has any mass, but it's the words that we use. So the language here is really critical. Your course grade is a weighted average on all of the different scores. Like lab is worth 20%. Homework is worth 10% or 15% depending on where you're taking it. Final is usually worth around 25. Some people make the final 50%. That's a lot of stress.
That's a lot of weight.
That's a lot of weight on the final, and that would be pretty stressful. But what scientists have done over the last 100 or so years have determined and calculated the weighted average of each atom on the periodic table, each element on the periodic table. And they take the percentage and they weight each percentage by how abundant it is, how much there are present.
So the atomic weight being this weighted average of all the masses in AMUs of the naturally occurring isotopes of an element. So for example, if you look at a sample of boron, you have 19.9% is boron 10 has a mass of 10.0 AMU, and boron is 80.1% boron 11 and has a mass of 11.0 AMU.
So just looking at this conceptually, I'm going to say that since I have way more boron than boron 11 than boron 10, it makes sense that the periodic table has a mass of a weighted average of 10.81. That large fractional amount indicates that there's more of the heavier atom present. Okay. Well, there's a way to calculate this.
Mm-hmm.
And I did my table thing, guys. Here you go. Students, you don't have to do it out this way. I'm just trying to be like super clear. So if I look at the isotope we're looking at, boron 10, it has a weight of 10 AMUs. I'm going to multiply that by the percent abundance divided by 100, which is the relative abundance, and I'm going to get a number. And I'm going to do the same thing with boron 11, the atomic mass of, and I'm only going to 3 sig figs, folks. I'm not doing a lot of decimals that you can get, which is what these asterisks means. You can use scientific numbers that have 8 decimals. I'm not going to do that, and neither do the students have to. So at 11.0 AMUs times 0.801 equals 8.81. Add these up, and that comes up to pretty close to what we see in the periodic table. I just didn't take the 7 decimals in order to get us there. So that's how you calculate a weighted average based on the percentages of the isotopes. Okay. Just to say another thing, the percent divided by 100 is equal to the relative abundance, is another scientific term we like to use.
Are there any units on that relative abundance?
No, there's no units on relative abundance.
Good to remember.
Yeah, it's a percent divided by a number.
Mm-hmm.
So, okay, so atomic weight, just to repeat, is the weighted average. Remember, it's not just the simple average, it's the weighted average of the masses in AMU of the naturally occurring isotopes of an element. So here's an example here.
So for example, if we take a look at chlorine, and we'll find chlorine is composed of 75.77% chlorine 35 and 24.23% of chlorine 37. So if we do the calculations out for this guy, we can take our 75.77% divided by 100 to get that relative abundance and multiply it by the AMUs for chlorine 35. Do the same thing for chlorine 37, 24.23 divided by 100 times its AMUs, and you'll see you'll get 35.45 AMUs for that weighted average for chlorine.
And this is the sort of formula you'll see in most textbooks. So this is the abundance, the percent abundance divided by 100 times the weight that they give you. Mm-hmm. A lot of textbooks, a lot of examples like to put lots more decimals on there. And we're just keeping the decimals to a minimum to keep the confusion down. And we're going to repeat the same thing with the other isotope with the percent abundance divided by 100 to get the relative abundance times that weight that scientists have looked up. These masses for that atom, scientists have weighed out the neutron to many more decimals of the AMUs. That's where those masses come from, and it's not an even number. And they calculate a weighted average, which for chlorine is almost, looks like the divide by 2, but wait a minute, it's chlorine 35 and chlorine 37. So chlorine 35 has 2 fewer neutrons than chlorine 37. Yeah. So it's not a divide by 2 thing going on here too.
Yeah, if it was divide by 2, it would be 36.
Yeah. Do you see how that works? So these values that we're using are based on very, very precise science values determined by scientists who worked a lot harder than me on it. Okay.
So we don't have to know how to figure out those percent abundances.
No.
Those would always be given.
You'll be given, good point, you'll always be given the percent abundance and you'll be given the masses to the correct number of significant figures. I'm not going to make you work backwards and figure that stuff out. But if you take another class, I might be able to do that, but not in this class. Okay, so chlorine on the periodic table will appear as atomic number 17 protons, but a mass number of 35.4527. Boy, that's 4 decimal places. That doesn't mean we have a fractional number of neutrons. It's the weighted average of all of the isotopes in that scoop of an element. So if we look at this periodic table that I got from the internet, let's study these. Look at this. Hydrogen is to 4 decimals. Look at beryllium. I've never seen that to 5.
Look at fluorine there. That's a long.
Those are a lot of decimals. And then we go down here to polonium, actinium, or astatine, and
Radon.
radon. I gotta put my glasses on. They don't even have them. Oh, wait a minute. Those are highly radioactive. Nobody wants to work with them. And this is obviously an older periodic table. And I say obviously to us because we know elements all the way up to 118 have been acknowledged as existing. I won't say discovered because they don't exist for very long. So all the way up to where this would be element 118 over here. All of these will be in a more updated or recent version of the periodic table. Be careful what you get from the internet. All right, so we're going to give you in the course, somewhere you could probably already printed it out, your periodic table should have only 2 decimals just to make it simple. So every one should have 2 decimals, except for the radioactive ones.
Yeah, they'll just be in parentheses.
Another common isotope is that of carbon. It has 3 isotopes, carbon 12, carbon 13, and carbon 14. And carbon 14 is what they use for carbon dating.
Wait, carbon atoms can find a date?
John, it's not a website. It's what they use to determine how old organic materials are. Anyway, we're joking, but truly, carbon 14 is very commonly used to date. Oh, that does sound so funny. To find how old organic materials are, like clothing from Egyptian tombs, things like that. Mm-hmm. On the periodic table, you're going to see it with the atomic, well, on this one I have the atomic number as 6 and the mass as 12.01. And keep in mind that mass is going to be the average atomic weight, and it's a weighted average. Okay? And the weight is always going to be larger than the atomic number.
So carbon must be almost all carbon 12 to be 12.01 for its weighted average.
Yes. It must have just tiny amounts of carbon 14 and carbon 13 present in it. Indeed. Very good, John. I forgot to mention that. Okay.
So hydrogen has 3 isotopes here. So if we look at a glass of water with some ice and liquid water, so hydrogen H1 basically has one mass number of 1, atomic number of 1, so meaning it has 1 proton and 0 neutrons. H2 is denoted with 2 for mass number, 1 for atomic number, meaning it has 1 proton, 1 neutron. And H3 is denoted with 3 for mass number, 1 for atomic number, meaning it has 2 protons and 2 neutrons and 1 proton. So each case, hydrogen has 1 proton and goes from either 0 neutrons to 1 neutron or 2 neutrons.
So, looking at this picture over here, I see that it has liquid water, H2O. Does that mean it's mostly the H1 and then D2O is mostly the deuterium? Does that little bit of extra mass make the D2O, solid D2O, sink?
Indeed it does. The mass of, it's not twice the mass, it's just 1 more neutron. But remember how tiny the atoms are? When you have an ice cube, which might be a scoop of atoms, it adds up a lot. And all of those neutrons will add up to make solid ice actually sink. If it's made with deuterium. So D2O will sink, but as we know, H2O floats when it's frozen, which makes great for ice fishing.
And to find a solid chunk of D2O, I would have to do some serious lab work, right?
You would get some serious lab work, and it would cost a fortune.
But I can't do this at home in my freezer?
Nope. One of the things that's called, that tritium is called, that's the isotope of hydrogen that's used in bombs, and it's called heavy water when you use tritium. And go ahead and Google that. You'll find some really interesting things. I grew up watching an old TV show that had some prisoners in a camp called Hogan's Heroes, and I remember watching them as a young child. I should say my parents told me about this show, but they would carry the heavy water across camp. I never knew that I would be teaching this topic back then. Heavy water really is much, much heavier than regular water, and it's very hard to carry around. Okay, so those are 3 important isotopes of hydrogen. Of course, H2O is the one that you're going to get most commonly. In fact, what does it say in the periodic table? The atomic mass of hydrogen is 1.00. Wait a minute.
7, 8, 9.
Something like that. So 7, 8, 9, whatever it is, something like that. It's got mostly hydrogen 1 present in a scoop of hydrogen.
And I think it's only hydrogen that uses a special symbol for its isotopes.
Yeah, you're right with that. Yeah, deuterium is the only one that does that. Yeah. That I know of, but I'm not a nuclear scientist either. So
the if you look on your periodic table, you'll see in the square you'll have the atom symbol, usually in the center, though every periodic table is a little bit different, so you may have to adjust this. You'll also see the atomic number, this typically at the top, though not always, and then you will see the atomic weight.
These are often reversed. It depends on the periodic table you buy, get from the internet, whatever. How do I know which one's always going to be the atomic weight?
Well, the weight includes all the protons and neutrons, so it will always be the biggest. And it is always the one that has a decimal in it as well.
So here's a Thinker Buddy question, which is something you might see something like this on a quiz. So pause and think. Why is the atomic weight of aluminum not a whole number? John, do you want to give me the answer?
Well, I think it has something to do with that weighted average we talked about earlier.
Yes.
So with the different number of isotopes for aluminum, if we take the percent abundance and calculate the relative abundance and multiply it by each of their individual weights, we can find out what the overall average weighted is.
I didn't write a complete sentence there, but I'm summing up what you were saying to me.
I was going to point that out and maybe deduct some points.
I know, because I'm the first one to deduct points when it's not a complete sentence. So, but taking shorthand, isotopes and weighted average is the reason why you see a not whole number in the periodic table. And if you haven't figured this out yet, what we really want you to get out of this whole thing is not necessarily how to worry about the calculations. It's about understanding the number that you see represents a scoop of that element. Go backwards. Can't go backwards. So anyway, we'll move forward and go with that and just deal with it. Maybe we can edit that out later. If we can't, oh well. All right, so this is a Thinker Buddy. I'm going to give you a chance to hit pause, and now we're going to try to work this out together. So guys, help me out here.
So we have 2 naturally occurring isotopes of antimony.
No, it's okay.
We have 121 and 123. Okay. So I see their natural abundances. I know that to solve this, I need to multiply the mass of each isotope by its abundance, divided by 100. So we have 120.90 AMU, and we're going to multiply that by 57.50 over 100. Okay, put that in parentheses, and then we're going to add to that the same thing for the 123 isotope. So we will do 122.90 AMU times its abundance, 42.50, divided by 100. Okay, and then
be careful with those parentheses in your calculators.
And know that this is the weighted average. Some people are tempted to divide by 2 even after this. There's no dividing by 2 in a weighted average. So you're just going to do this calculation like this. You will get 69.52 AMU plus 52.23 AMU. 23,
okay.
Added together, we get 121.75. Note that there are 2 decimals at 2 places after the decimal in the sig figs, so our addition would have 2 places after the decimal.
Oh, I could prove that by adding it this way.
Mm-hmm.
That is true. It's always a good practice to line them up in columns.
Line up your sig figs for the addition rule being different than your multiplication rule.
Sorry, I'm adding slowly here. Kind of like watching paint dry. Okay. All right. So
Good.
any questions, post, ask. We're all here for you.